I'm going to choose the route of multiplying this out, distributing it out first to rewrite it and then apply our derivative rules. So I'm going to rewrite this, distributing the x cubed in to get 3x to the 5th minus 10x cubed. Then I'm going to take the derivative, and we're using that shortcut. So I'm going to take my exponent and multiply it by the coefficient. So I'll have 3 times 5 and get 15. And then subtracting 1 from the exponent, that's going to be a 4. From that, now I'm looking at this derivative, 3 times 10, I'm looking at 30x, and when I subtract 1 from the exponent, I'm at 2. So if that's all I cared about, great, I'm done. But today, we're going to be exploring what else can that derivative tell me. So we know that that derivative, if we pick a particular value of x, can tell us the slope of the tangent line at that point. But today, I want to talk about something that I'm choosing to call roller coasterology. I don't really know what this function looks like. Well, I secretly do, but we'll come back to that in a second. For now, I just want to talk about a totally arbitrary function. And I promise I'm not going to make you graph its derivative. I know that's something that we were talking about another day. But if I have some function, let's say that looks like this. If I wanted to graph the derivative, then the points that stand out in terms of my first place, if I have to sketch the derivative, is always looking for the places where I'm 100% sure I know where what the slope is. And those are always going to be the places where the slope is exactly 0. Now you'll notice oh, I got another one hiding over here. I was kind of standing in front of it. So you'll notice at each of these places where my slope is exactly 0, they represent either a high point relative to the points around it or a low point relative to the points around it. So we're going to call these points where it's the highest value relative to everything around it. We call these a relative maximum. Now, because Ben's class hasn't gotten here yet, I'm not sure which word he's going to use. We've got 2 different words that we can call this, either a relative maximum, or we can also call it a local maximum. They mean the same thing. It's just 2 different words for the same thing. These places where my point is the lowest value around it, we're going to call those a relative, or I'm just going to abbreviate that REL for a relative or local minimum. Same deal down here. This would be a relative or a local minimum. If I take a step back and I look at the entire graph, if there is a place on the graph that is the highest point on the graph, then we're going to call that a global or absolute maximum. So when I look at that graph, I see that this point over here is the highest overall point on the entire graph. So we call this, it is a local maximum because in its local context, meaning just comparing it to the numbers around it, it is a maximum. But this is also this also represents a global or absolute maximum. Now again, if I take a step back, so I'm looking at the whole picture, I might want to know, is there a place on the graph that is the lowest spot on that graph? And I'm going to argue that there kind of isn't. because my graph over here, although this graph didn't just stop right there. It stopped because we hit the edge of my whiteboard. And we don't really know this one, you know, it also kind of stopped over there because it hit the edge of my whiteboard. So if I looked at this entire function, I would have to say there is no absolute minimum based on the picture. We'll have more fun with that later. But now to thinking about this graph, because we won't always have the graph, sometimes we're just working with a function, like on the other side of my whiteboard. So, there's a question about, but would there also be no absolute maximum? So if this represents everything interesting that's going on in the picture, then I can confidently say that's an absolute maximum, right? Because if this represents everything interesting, then we're going to assume that's what's happening. We'll come back to that in a second. Most of the time, we're not going to be deciding absolute max and min with a picture. Most of the time, we'll actually have a function that we're working with. So we'll do that with some functions in a minute. But where I want to go is if I don't have the picture, and the only thing that I know is the places where the slope is equal to 0, how can I figure out whether around that place where the slope is 0, if it's the lowest thing around, meaning a relative minimum, or the highest thing around? And we're going to use the derivative to figure that out. So if I look on the left-hand side of my m equals 0 here, all of these tangent lines have positive slopes. And thinking about the picture, if my tangent lines have positive slopes, then that means we're going up. So in the scheme of what I'm calling roller coasterology, if I was going up on a roller coaster and then I was going down, I must have hit a relative max at the top. If I was going down on a roller coaster and then up, I must have hit a relative min. If I was going up on this roller coaster and then down, I must have hit a relative maximum. And we're going to use that idea of when are we going up and when are we going down to figure out when we have a relative max or min without drawing a picture. So I'm going to flip this around and go back to that problem that I had you all take the derivative of. Well, just like if I had to sketch a graph of the derivative, or if I was looking at it graphically, that first thing that I'm looking for is anywhere where the slopes are 0. So I'm going to start by setting our derivative equal to 0. And if I have something where my derivative is equal to 0, personally, I'm hoping that it factors. And looking at this, I can pull a 15 and an x squared out of both terms. So if I do that, and I've got 15x squared, then from here, I have an x squared left, and from here, I have a 2 left. Meaning if I distributed that back in, I get what we started with. So my next step, and I'm going to take Haley's advice, I'm going to make a sign chart. I'm going to maybe do my sign chart a little bit differently than how it may have been presented in class, not sure. I'm sticking with one of the methods that our book gives us. And I want to know, thinking about that roller coasterology, where am I going up and where am I going down? This is telling me that I have, well, let's see, 15 is never equal to 0. The x squared is 0 when x is equal to 0. And this, if we're clever, we're going to get that x is equal to positive or negative square root of 2. And my sign chart, I'm going to call a number line. And I'm going to label my number line with f prime. And the reason that I'm doing that is sometimes we might be looking at the second derivative, sometimes we might be looking at the value of the function, and I want to make sure I know what I'm talking about. So I'm going to label this as f prime. And onto that number line, I'm going to put every value of x that makes that function 0 or undefined. In this case, we don't have to worry about the undefined part. So on my number line, I'm going to have negative square root of 2, 0, and the square root of 2. And what I need to know is in each of these regions, right, I've now split my number line into 4 parts. In each of those 4 parts, what's the value of f prime so that I know if I'm going up because the derivative is greater than 0 or going down because the derivative is less than 0. So I'm going to pick some test points here. I don't know what the square root of 2 is, but I do know it's bigger than 1. So I'm going to test the point x equals 1. I'm going to test x equals negative 1. I'm going to pick something I know for sure is bigger than the square root of 2, like 10. And I'm going to pick something out here like negative 10. And for each of those test points, I want to plug them into f prime. So it doesn't matter which version of f prime we plug them into. I usually prefer to plug it into the factored form. So if I start with negative 10, negative 10's, well, we're squaring it. It's got to be positive. So 15 times negative 10 squared, so far we're at a positive. If I take that negative 10 and I square it, now I'm at 100 minus 2. Well, that's 98. So for sure, I've got a positive number times a positive number. And overall, my derivative is positive, which then if I think about what's happening to the function, that means the function must be going up. And like I said, I labeled this as f prime so I can remember for myself. I'm plugging each of these numbers into the derivative, not the original function. But up here, I'm going to show what the function itself is doing. So I know my function must be going up. If I plug in x equals negative 1 to the derivative, negative 1 squared, now that's positive, times 15, still positive. Negative 1 squared is 1, and then minus 2, so I'm at negative 1. So I have a positive times a negative, and that's going to give me a negative, which means my function must be coming down. If I plug in 1, anything squared is positive, so I can kind of just ignore that part over there. 1 squared minus 2, that's still going to be negative. So my function is going down. And then out here, if I plug in positive 10, 10 squared is positive, 10 squared is way bigger than negative 2. That's going to be positive on my derivative and going back up. So in the scheme of roller coasterology, it's not really a word, I made it up. Actually, I shouldn't take credit for it. I think Grant made it up. Okay, so I'm going up and then going down. So if I was going up and then going down, this point right here must have been a relative maximum. Here I'm going down, but then I'm going down some more. So I wasn't at a maximum or a minimum yet because I'm still going down. Thinking about when x equals square root of 2, I'm going down and then going back up. So this must have been a relative minimum. So there are a couple of different ways that we might get asked a question here. So some of the common ones include certainly to find all relative extrema. That's a question we might get asked. And if that's the question we were asked, then we're looking for stating that x equals negative square root of 2 is a relative maximum, and x equals positive square root of 2 is a relative minimum. I might get asked to find the intervals on which f of x is increasing or decreasing. If I'm answering this second question about intervals on which f of x is increasing or decreasing, we're always going to give our answers as open intervals, meaning parentheses, not square brackets. And the reason is, looking at this, so let's pick one of these values. If I'm actually at an x value of negative square root of 2, the derivative is neither positive nor negative. It's actually 0. So negative 2 would not get included when we're talking about increasing, and it wouldn't get included talking about decreasing. So let's answer this first one. Let's suppose we were looking for the intervals where f of x is increasing. Thinking about my number line here, we're increasing in this zone where my derivative is positive, and also in this zone where my derivative is positive. So we're increasing. Now that extreme edge over there is negative infinity, and this extreme edge over here is positive infinity. So I would say that I'm increasing from negative infinity to negative square root of 2. I'm always using open brackets on these. Also, we're increasing from square root of 2 to positive infinity. For the intervals where we are decreasing, I'm going to be decreasing everywhere in here where the values of my derivative were negative. But again, I want to be careful to list this using open brackets. So this is going to look like negative square root of 2 to 0 union 0 to positive square root of 2. And it's important to sort of punch out that hole at 0, because at 0, my derivative is neither positive nor negative. So let's say that I had to graph this thing. So for starters, if I really was trying to graph this, like the whole thing, I would want to make sure that I include all the intercepts. So those x-intercepts are happening whenever the derivative is, sorry, that word came out of my mouth. The x-intercepts are happening whenever y is equal to 0. And I know I said y, I'm pointing to f of x. That's because f of x is y's grown-up name. So whenever y is equal to 0, those are our x-intercepts. So I'm looking at x-intercepts of 0 and plus or minus the square root of 10/3. I don't know what the square root of 10/3 is. I'm just going to label it square root of 10/3, negative square root of 10/3. Now I'm going to use my roller coasterology to fill in what this graph looks like. So I know that I'm going to have a relative maximum when x is equal to negative square root of 2. Well, I don't know what the square root of 2 is, and I don't know what the square root of 10/3 is, but 10 over 3 is bigger than 2. So for sure, whatever square root of 2 is, it's somewhere in here. Sorry, negative square root of 2. And whatever positive square root of 2 is, it's somewhere in here. And I tried to do that so that this would line up pretty well, but I missed a little bit. So I know that in here, I've got to be going up until I get to the square root of 2. And then I know that as I approach 0, I was coming down, but I keep going down. And then when I get over here to positive square root of 2, I'm going to start going up again. So this should kind of look like this. Now, I'm going to use my pre-calculus skills to know that right around 0, this should look like a cubic. So right around 0, this should have a little bit of a squiggle to it and kind of squiggle through there. We'll talk a little bit more about that squiggle in a bit. But that's approximately what our graph would look like. And anybody who's freaking out about having to graph things by hand, your TAs are very forgiving. It doesn't have to be perfect. Just try to make it smooth and not really like sharp points everywhere. Just kind of try to smooth it out a little bit. But they're going to give you the benefit of the doubt if you've labeled things well. Speaking of labeling things well, I chose a really terrible problem in terms of numbers here, but if I were really trying to label things well, I should probably label these points, but I'm going to label it the lazy way and say that's the negative square root of 2, comma, f of negative square root of 2, because I don't want to plug in the square root of 2 to that. Same thing down here. I'm going to have positive square root of 2, comma, f of square root of 2. Given time, energy, and sufficient monetary motivation, I suspect that you could plug the square root of 2 into here and get a y value. Cool, let's do our derivative. So, just going to get rid of my f and g, give myself a little more space. Since I know I'm doing a quotient rule, I'm going to get all of my pieces ready. And whole thing squared on the bottom. So I've got x squared plus 1 squared on the bottom. And then on the top, I'll have the derivative of x and get 1. And then x squared plus 1. I'll leave the x alone. And then the derivative there is looking like 2x plus 0. Now, I didn't actually ask us a question beyond this, but I want to look at the same 2 questions that we did on the previous problem. So I want to find and classify all relative extrema, meaning I'm looking for the maxes and mins, and to get the intervals where it's increasing and decreasing. So I would start by setting this equal to 0, but that's a little bit messy, so I want to clean it up first. Looking at this, 1 times x squared plus 1, if I distribute the 1 out, I just have x squared plus 1. And here, I'll be subtracting off x times 2x, so minus 2x squared. And that whole thing is over x squared plus 1 squared. And it looks like on top, I can clean it up a little bit more and call that 1 minus x squared over x squared plus 1 whole thing squared. If I set this equal to 0, so that I'm looking for those places where my tangent slope is 0, those are the places that are either going to be tops of my graph or bottoms of my graph, hopefully. So looking at this, if I set this equal to 0, the denominator is never 0 because x squared plus 1 can't be 0, but the numerator is 0 at 1 and negative 1. If I get my number line going here for f prime, that means the numbers on my number line would be negative 1 and positive 1. If I think about some test points here, I'm going to choose 0, 2, and negative 2. Well, if I plug 0 into my derivative, and it doesn't matter which version of the derivative we plug it into, I'm going to choose this one. If I plug in 0, then my numerator is equal to 1, and my denominator is also equal to 1. 1 over 1 is positive, which means I know my function should be going up. If I plug in x equals 2, then on the top, I'd have 1 minus 2 squared. Well, that's a negative number. And on the bottom, here's a trick about quotient rule. The bottom is always going to be positive, because no matter what I put down there, we're squaring it. So I actually really only care about the sign on the top. The sign on the bottom will always be positive for these. So I know that overall, when I plug in 2, this is going to be negative, and my function is coming down. Over here at -2, if I plug in -2, same thing happens. -2 squared is going to give me 4. 1 minus 4, I've got a negative number on top. So my function is decreasing. That's enough in my roller coasterology to know that when x equals -1, that is a relative minimum. And when x equals +1, that is a relative maximum. So I've got a relative minimum when x is equal to -1. I want to point out something really subtle in the way that questions can be asked. So sometimes you might be asked when, that question, when is there a relative minimum? And typically if it's asked as a when question, we're going to give the answer as just the x value. But if I am asked where is there a relative minimum, then if the question is where instead of when, we're usually going to give coordinates. I'm going to give the location. So this would be -1, comma, and then I would need the y value at -1. So this could also be phrased like if it's sort of a fill in the blank on an online homework, rather than actually asking with a question of where. Sometimes it will prompt with the word at. None of this probably matters on your written homework or on a written quiz or test, but if you're getting an error message when you're trying to put it in online, it might be that difference between, was it expecting both an x and a y coordinate, or was it only expecting an x? So to finish this off, let's go ahead and give the y coordinate. And if I want to know what y equals, I need to go back up to the beginning where we had a y equals. And if I plug in -1, then I'd have -1 over -1 squared plus 1. So I'm looking at -1/2. And that's my relative minimum. We're going to have a relative maximum at 1, comma, and if I do the same thing here, but I switch my -1s to +1s, I'm going to get a 1, comma 1/2. And then we can say that this is increasing on, and the only place we're increasing is from -1 to 1, but we are decreasing on -infinity to -1 and from 1 to +infinity. So looking at this thing, if we want to talk about absolute maximum or minimum, oftentimes these questions of absolute maximum or minimum are specifying a particular interval to look on. So for example, if I take this and I take a step back, so I'm looking at the whole thing, I already said that this is the highest point on the entire graph. So this would be the absolute maximum if I look at the whole thing. But maybe this function has some context where it only makes sense to look at the portion of the graph from, let's say, here to here. So if I restrict us to only looking at the part of the graph that is in that particular window of x values. Now, when we look for that absolute maximum or absolute minimum, I only want to consider inside of this window. And if I only consider inside of this window, this point right here is the highest point. And this point down here is the lowest point. And we have this absolute value theorem in the textbook that says if we restrict the domain so that we're only looking at a little window of the graph, then those absolute maximum and minimums can only ever occur at one of our relative extrema or at the end point of the interval. So even without a graph, we're going to be able to figure out what those absolute maximums are based on thinking about finding those relative extrema and checking the endpoints. So let's do a problem where we're finding absolute maximum. Now this question of find the largest y value if x is between 0 and 2 would probably more likely be phrased as find the absolute maximum on 0 to 2. So we're going to start off the same way that we started our other problems, meaning if we're going to find relative maxes or mins, we first need to take the derivative and set it equal to 0. If I'm looking at this function and I take the derivative and I take that exponent, bring it down in front, so I'll have 4/3 x to the, and when I subtract 1 from 4/3, I'll have 1/3 left. I'm going to multiply that 1/3 down in front, so I have -4/3 x to the, and when I subtract 1 from the exponent, I'll be at -2/3. The derivative of 1 is 0, so we can leave it alone. I'm going to set this whole thing equal to 0 and hope that something factors. I don't think we've done any problems that required this kind of factoring, but hopefully you've seen some of this kind of factoring in your pre-calc classes. So for sure I can pull out that 4/3. Since I have two x's, I can also pull out an x. And what I'm going to do is I'm going to pull out the x with the smallest exponent. And by smallest, I mean furthest to the left on the number line. So I'm going to pull out 4/3, and I'm going to pull out x to the -2/3. It's kind of awkward to factor this way, but I know that if we were to undo that factoring, I would need that 4/3 x to the -2/3. When it gets distributed in right here, I need to get 4/3 x to the 1/3 back. So I know that this is going to need to be x to some sort of power. And I know that when I distribute this in, I would add those two exponents because I'm multiplying two things with the same base. So -2/3 plus what is going to give me 1/3, and that plus what is 3/3. From here, I pulled everything out. I pulled the 4/3 and the x to the -2/3, so that's just going to be a -1. Looking at this, I'm going to rewrite that to say 4/3 x to the -2/3 times, well, 3/3 is also known as 1, so this just says x minus 1 is equal to 0. So now I'm thinking about what values of x would make this equal to 0. Well, if x equals 1, for sure, that's going to make this equal to 0, my derivative. And I want to be really careful here because I can't actually plug in 0 for x. to this part of my derivative. And the reason is, if I tried to plug in a 0, that negative in the exponent is really telling me that that's x to the 2. This thing is 1 over x to the 2/3. So if I tried to plug in 0, I would be dividing by 0. So a value of 0 makes my derivative undefined. So x equals 1, we would call a critical point. X equals 0, we call a critical number. And I'm calling it a critical number because it makes my derivative undefined. F prime of 0 does not exist. And so sometimes there's that subtle distinction between looking for critical numbers, which is anywhere that makes my derivative 0 or undefined, versus looking for critical points, where typically we're looking for places where it's actually equal to 0. Okay, just a little subtlety there. Because we want to find the absolute maximum on 0 to 2, process-wise, our step 1 was to find the critical points by setting f prime of x equal to 0. And from this, the only critical point we got was that x equals 1. Our next step, in terms of finding the absolute max or mins, is that we want to check the y values at the endpoints and the critical numbers. So we're going to take those endpoints of 0 and 2 and that critical number of 1 and plug each of those into the original function to see which one gives us the largest value of y. I will admit that I may have chosen poorly with an endpoint of 2 because I don't know what the cube root of 2 is. Will you all forgive me if I change that 2 to an 8? Just because I know what the cube root of 8 is?
Sounds good to me.
Great, let's make the problem easier for ourselves. So fix it in your notes so you don't look back later and you're like, why the heck were we plugging in 8? We're plugging in 8 because I'm changing the problem. Okay, we're going to use 8 instead. So we're going to check f of 0, f of 1, and f of 8. And I know functionally you get to use a calculator, but you know, I don't want to worry about that. So if I plug in 0, then 0 to the 4/3, well, that's 0, and that's the more 0, and I get 1. If I plug in 1 raised to any power, it's just going to be 1. So I've got 1 minus 4 plus another 1. It's going to be -2. And now if I look at 8, the cube root of 8 is 2. This one I'm going to write out. The cube root of 8 is 2, so that would be 2 to the 4th minus, again, the cube root of 8 is 2. So 4 times 2 and then plus 1. So 2 to the 4th is 16. Minus 8 brings me down to 8, and then plus 1 takes me up to 9. So if I'm looking for the absolute maximum on 0 to 8, 9 is the value that is the absolute maximum. When we talk about concavity on a graph, one of the ways that we can kind of conceptualize that is places where my graph is kind of curved up so that if it were raining, it would collect water. So if it were raining, the graph over here would collect water in this place. We call it concave up. And this portion over here, if it were to rain on top of it, it's kind of like an umbrella, and the rain would just slide down the sides. It wouldn't collect. This portion of the graph is concave down. We can also use the words concave and convex, but our textbook uses concave up and concave down. Now, mathematically, if I don't have the graph already, we need a way to figure out where this is concave up and concave down. And once again, derivatives to the rescue. So if I think about this graph and I draw in some tangent lines for myself.
Excuse me. I don't think the we can see the lines because of the color of the.
Got it. Okay. I think they'll magically appear for me when I draw them better. Thank you. So if I think about my tangent lines on the graph, and I think about a tangent line over here, I'm going to make a fake slope for that line. So I can see the dots. I don't know if you can, but that's about 1, 2, 3, 4. That's about a slope of -4. Now, if I come down here and look at this tangent line right there, that's a slope of about -1. And I know that down here at the very bottom, we already know that our slope should be 0. Now, if I think about going up the other side, that tangent line right there, that's a slope of about that's about a slope of 3. And maybe right in here, by drawing that tangent line, that's a slope of, let's say that's a slope of 4. Then if I get over here, that's a slope of 2. And I know that up at the top, I'm back to a slope of 0. Well, if I think about how these slopes are changing, as I move along the graph, my slope over here started out as a negative slope, but to get from -4 to -1, my slope got bigger, right? The actual number got larger. So from -4 to -1, my slope was increasing. Well, from -1 to 0, that's also an increasing number. And from 0 to 3, my slope is also increasing. And from 3 to 4, my slope is also increasing. From 4 to 2, that's the place where my slope, everywhere along here, my slopes were getting bigger. And then once we hit this point on the graph, now my slopes are getting smaller. If I kept these slopes going, that up there at the top was a slope of 0. If I sketch that in, that's a slope of -1. If I sketch this in, that's a slope of about -3. I'm going to sketch this in down here, that's a slope of about -5. So as I keep going from 0 to -1, from -1 to -3, from -3 to -5, those slopes everywhere in here are getting smaller. There are a lot of different ways that we think about the derivative in the context of 16a. And I would say if there's one thing that you work on kind of getting solid during 16a is that it's this idea that the derivative is telling me the slope of a tangent line. The derivative is also telling me how the function is changing, right? Am I increasing or decreasing? Well, that means that this idea of a slope getting bigger, well, if the slope is getting bigger, then my slope is increasing. But to decide if something's increasing or decreasing, we take a derivative. So this is telling me the derivative of the derivative is increasing. So my takeaway here, if to write notationally my derivative of the derivative, that we use 2 primes, so I can call that f double prime, or we can say the second derivative in this region, if it's increasing, my second derivative was positive. My second derivative being positive means we are concave up. Now over here, my second derivative, my slope of my slope, since it's getting smaller, my second derivative is negative. We say that that's concave down. So we're going to use that idea of looking at the second derivative of a function to give us more information about the graph. Not just are we going up or going down, but what does the curvature of the graph look like? Is it curved up or curved down? And now that I want to talk about concavity, I want to go ahead and take another derivative, or that second derivative. So I'm going to get the f double prime, and let me leave just a little bit of space here. F double prime of x. 4 times 15, that's got to be 60 x cubed minus 60 x. Armed with my function, the derivative, and the second derivative, I want to draw the best sketch of this graph that I possibly can. To do that, I want a sign chart or a number line, not just for my first derivative. Nope, I don't want to put it over there because I want more space. I want to draw that sign chart or the number line, not just for my first derivative, but also for my second derivative, so that we can talk about concavity. So there's a question in there about, so a second derivative is an example of a higher order derivative. We can also take a third derivative, a fourth derivative, a 17th derivative. We can keep going. And so that phrase higher order derivative just means anything more than the first derivative. This part's already in your notes, your number line for f prime. And we had 0, negative square root of 2, positive square root of 2. And if I'm remembering correctly, this was a positive, negative, negative, positive. And then I had mentioned that that means we know some things about what's happening with the function itself. And that meant that we were going up and then down some more, and then back up. Well, now let's take a look at that second derivative and get a number line going for it. So if I look at where my second derivative is equal to 0, I'm hoping we can factor something out. And here I can factor out a 60x. Once I do that, from here, I'm looking at x squared, and over here, I have a -1. So I can keep factoring that and say that's 60x times x minus 1 times x plus 1. For my sign chart for my second derivative, and I realize those two are really close together and not showing up very well on screen as a second derivative. There's my second derivative. To this sign chart, I need to have 0, 1, and -1. I'm going to give myself just a little bit more space here, because what I like to do, the reason that I've kind of stacked these up, is that I like to put everything in its relative position in terms of the x values, so that when I go to sketch my graph, I kind of already have it put together. So I need 0 to be one of the critical numbers for my second derivative. It's also a critical point because it's a place where my derivative is actually equal to 0, not undefined. So I'm going to need 0, and then 1 and -1. Again, I don't know what the square root of 2 is, but it is bigger than 1. So 1 and -1 would live in there. To get to see what's going on with my second derivative, I would need some test points. So I need some numbers to plug in here. Now don't get too hung up on the actual values, because I only care about whether it's positive or negative. So if I choose a point in here, and I would say, if you're better with decimals, choose decimals. If you're better with fractions, choose fractions. I prefer fractions. So I'm going to think of test points of 1/2, 2, -1/2, and -2. And for each of those test points, I care about what's happening in my second derivative. So if I look at my second derivative at -2, I'd have 60 times -2. And because there's a bunch of pieces, I'm just going to keep track of the signs. So I've got 60 times -2, so that would be a negative. -2 minus 1, that's another negative. -2 plus 1, that's another negative. A negative times a negative times a negative is going to give me a negative for my second derivative, which means up here on the graph, I know that I would be concave down. Now let's look between -1 and 0. We're going to be plugging in x of -1/2. So f double prime of -1/2. I'd have 60 times -1/2, that's negative. -1/2 minus 1, also negative. -1/2 plus 1 is positive. Negative times a negative times a positive means in here I'm positive, so we'd be concave up. Now I'm going to plug in 1/2. So f double prime of 1/2. 60 times 1/2, that's positive. 1/2 minus 1, that's negative. 1/2 plus 1, that's positive. Overall, I'm at a negative. More concave down. And then don't have space for it, so I'm just going to erase this and do f of 2. Sorry, f double prime of 2. So if I plug in 2, 60 times 2, I'm at a positive. 2 minus 1, I'm positive. 2 plus 1, I'm also positive. So I'd be positive on my second derivative, concave up out here. Okay, now we're going to put all that together to put this onto a graph. But I mentioned, or someone else said, can we do a detailed graphing problem? So Kuba has really specific instructions for a detailed graphing problem. We're going to have to do, we're going to have to look at increasing, decreasing, concave up, concave down. We're going to need to know those relative maxes and mins. We're going to need to look for inflection points. We'll go there momentarily. And we're also going to need to show the x and y intercepts, any asymptotes, and talk about the domain and range. So if I go back to that stuff that we were working on for the first midterm, those asymptotes, domain and range, this is a polynomial. So my domain is all real numbers. If I multiply this out, it's an odd polynomial, which means my range has to go from -infinity to +infinity. Now for the fun stuff. When we did this a few minutes ago, or actually really like an hour ago, I found those x-intercepts for us by setting x cubed equal to 0, which gave us that one, and then setting this equal to 0, which gave us a positive square root of 10/3 and a negative square root of 10/3. Now we're going to sprinkle on the calculus. So I know that something interesting is happening at square root of -2, and something interesting is happening at, negative square root of 2 and -1, and then again at +1 and positive square root of 2. So I'm just going to mark those on here. Negative square root of 2 and 1 and 1 and square root of 2. So way out here on the left, I'm supposed to be concave up and increasing. I said concave up. That's concave down like a frown. So I'm concave down and increasing. So concave down, but my function is moving up. I'm going to keep moving up all the way till I get to -2. And I'm going to remain concave down all the way to -1. So I'm going to keep going up until I hit -2. And I'm going to remain concave down. But now between -2 and 0, my function has to be going down. So I'm coming down, but when I get to -1, my concavity changes, and now I need to be concave up. So I'm going to be concave up coming into 0. When I get to 0, I'm going to keep going down, but now I'm concave down. So I'm going to be moving down and have a downward concavity till I get over here to 1. Then my concavity is going to switch to concave up. Then I'm going to keep moving down until I get to square root of 2. I'm going to remain concave up, but now my function needs to be going up. So that is my detailed sketch of this graph. And then we could do all those same things we did before. We listed the intervals where it's increasing and decreasing. We talked about here, I could do that same idea of intervals where we're concave down and concave up. And then the one extra thing that we haven't talked about yet, and I know I'm out of time, but this graph has 1, 2, 3 points of inflection. And in order to be a point of inflection, 2 things have to be true. 3 things. It has to be a point. So it can't be somewhere on the graph that's undefined or outside of the domain. Okay, that one was maybe given. It has to be a place where my second derivative is equal to 0. Check, -1, 0, and 1. And the most important part is a place where the concavity changes. So on either side of -1, my concavity changes. They have opposite signs. On either side of 0, my concavity has opposite signs. And on either side of 1, my concavity has opposite signs. On the graph, I think about those inflection points as kind of that little squiggle.